Micro.
Hello, good afternoon. Welcome to this panel session. I can see you, it's a pity, but I hope that everybody can see and will see perfectly the speakers. This is a specific panel session about urban and pre-urban transport systems. In this panel, we will speak about transport system. We will speak about climate change challenge. We will speak about adaptation, but mainly we will speak about planning and how to introduce the climate change challenge to the future, for the transport system of the future. We will see international experience, projects, tools. Really, we have 5 speakers with very, very interesting projects to explain. I suggest if you want to make questions, please use the chat. It will be better if you put your name and you specify from whom is this question. It will be easy to manage later the debate. I want to thank the RESCCUE organization to adapt the conference to this new normal. I think that it's such a nice initiative to maintain and to have the possibility to discuss about how climate change has putting us so many challenges that we can thank them for having organized. First of all, we will listen Luis Alegre. He is from the Metropolitan Transport Authority of Barcelona. He's the director of the Public Transport Infrastructure Plan and also for the Mobility Master Plan. He's driving also managing the Mobility as a Service project. He's civil engineer graduate and master in urban management, in mobility planning, and in financial management. So please, Luis, time for you. You can start when you want.
Okay, thank you, Elisabet. Many thanks. I share my screen. Okay, I hope that you can see the screen. Hello, everybody. I hope all of you stay well. I am going to explain how in Barcelona metropolitan system are tackling climate change regarding mobility infrastructures. I must say that we have been participating in the RESCCUE project since the beginning. This is the scope of my presentation. First, ATM is an intergovernmental consortium created to coordinate public transport, consisting of the Catalan government, metropolitan area of Barcelona, the city of Barcelona, and the AM2, that is a group of municipalities with public transport. During the last years, between 2006 and 2012, we reduced or decreased the energy consumption more or less 21%, and also we reduced the emissions of carbon dioxide. But the last 8 years, we have had an increase of the mobility with private car, and also a small increase of the CO2 emissions. What we decided to facing climate change in 3 topics: reducing emissions, and also, excuse me, and also planning the future and adaptation of the infrastructures. Today I'm going to talk especially about planning the future and adaptation of the infrastructure, but of course we have our mobility plans where we are working on reducing emissions specifically. The current risk in mobility infrastructures, well, of course, we have risk of flooding in the coast and also in some of our rivers. We have geological risk, rock falls and landslides, every more frequent. And also we have risk of fire, especially because of the rising of the temperatures. So we decided to study the climate dangers and risk to mobility. There are two kinds of risks, direct and indirect, of the dangers. The risk, there are direct, like high temperatures or maximum wind speed, but indirect, they are rising sea level, other flooding fires, for instance. We study the effects of this risk in our infrastructures, like insufficient drainage system capacities, floods in underground stations, damage to the road, decreased comfort due to climate, reduction of visibility, and then which impacts on mobility, alteration of the interactions, people's mobility, public transport services and private vehicles, freight transport, increased possibility of delays, accidents, and we study the cost, the socioeconomic cost. We built climatic scenarios, the filter maximum average temperature scenario in August, rainfall in autumn, and rainfall in the spring. And with these scenarios, we create the infrastructure risk maps, road and rail networks. For instance, road networks in areas with a maximum average temperature in summer, for instance, higher than 32 degrees. We propose 15 measures and 24 actions, two kinds of measures, short-term measures. They should take effect immediately or in the coming month, and medium-term measures. They should take effect in the next years. We work reviewing the regulation in all areas that will need to adapt, and the following infrastructures will be taken into account: road, railway infrastructure, port, and airports. For instance, short-term railway measures, some examples: slope with risk of erosion, erosion of bridges, tunnels, drainage works. Medium and long-term railway measures, stations meeting requirements, review recommendations for existing projects, regular operation of inspection systems. So we create this table that we have the proposed measures, we have a description of the action, the kind of solution, technical, operational, maintenance, cultural or regulatory, the mode of transport, road and railways, the kind of infrastructure, existing or new. Then we work making a cost-benefit analysis, cost of not intervening. The following items were monetized: victims, increase in travel time, alternative services, and the cost of investing in adaptation. They have been assimilated into infrastructure replacement cost. We work on priorities of the measures. We work preventive adaptation actions cannot be applied indiscriminately, given that they would lead to excessive measures that are economically unacceptable. So we must prioritize actions and at the same time progress with risk management models. Criteria for prioritization measures were vulnerable points identified by previously documented incidents, points highly exposed to certain risks, for example, sections of infrastructure located in areas of preferential flows, points that would present a good cost-benefit ratio, taking into account one or more of these factors: alteration of the services, effect on a significant number of daily trips, or no alternative means of transport. The next step was defining adaptation, governance, and roadmap. Adapting the mobility system and road and rail infrastructures in particular must be conceived as a progressive process that can necessarily be reviewed and updated, and that can be modulated in line with actual climate change. The inertia associated with the long life cycles of mobility infrastructures makes it necessary to work in parallel on three levels: increase the resilience of existing infrastructure, encompassing actions on operations and maintenance, design and execute the new infrastructures incorporating criteria for adapting to the new climate scenarios, and establish a context that favors optimized management of potential risks and real incidents based on early warnings, sensors and monitoring systems, for example. At the end, we elaborate the new master plan for public transport infrastructures that is currently being drafted and has incorporated the short and medium-term actions proposed in this document for an amount of 173 million euros in the first phase and 74 million euros in the second phase. To finish, we decided to make a coordination group because it's a key aspect of the governing of the transition to a more resilient mobility system in coordination and collaboration between the different actors involved. To improve the early detection of possible situations of risk or vulnerability, a strengthened coordination to optimize management before, during, and after an incident, establish a homogenized record of incidents arising from climate episodes, and establish synergies and economies of scale to carry out joint preventive actions. To the right, you have the main actors involving. So, to the end, this is the work regarding infrastructures, and we have the work that we did with the mobility plan of the region. All of them in an integrated way. And that's all for me. Thank you for your attention.
Thank you very much, Luis. I think that it was so interesting. You have put so many things on the table. I hope that later we will have time to discuss and to turn back to some points. For example, that related with the coordination. Now we are going to listen Núria Biosca. She's from the international consultancy firm IMC Worldwide. Núria is an engineer specialized in climate change, resilient infrastructure, urban development and building. Núria, you have more than 10 years experience as a consultant and manager in the international development sector. And you have been working around, I think that about 50 countries, Africa, South Asia, and Caribbean. I hope that we will see in your presentation some of these experience very well explained. Thank you. Come on, Núria, time for you.
Yes, thank you, Elisabet, for the introduction. I'm going to share my screen.
Mm-hmm.
So good afternoon, everybody. My name is Núria and I come from IMC Worldwide. IMC is a British civil engineering consultancy firm. We mainly work in developing countries, in particular in Africa, South Asia, the Caribbean, and the Pacific. We've been working a lot in climate resilient infrastructure over the last 5 years. And I would like to take this opportunity to present some of our climate resilient projects in the Caribbean. I will be talking about the methodology that we use to develop climate risk and vulnerability assessments, CRVAs, and in this case, on the road transport sector. So in this presentation today, I'm going to briefly explain the objectives of the CRVA process, the framework that we use, and I will also be sharing with you some of the outputs produced using GIS modeling.
Yes. Nuria, I'm sorry, but we are not seeing your screen. Perhaps you have a presentation, I think.
Oh dear. Okay. Can you see me?
Yes, we can see you, we can hear you, but we can see the presentation. And I know that it's a very interesting presentation.
All right, okay, sorry.
Perfect.
I kept talking, okay, fine. I can start over. Yeah, is it okay now?
Yes, it's perfect.
Okay, fine, sorry. Okay, I was on the second slide. So I was just mentioning that I will be explaining briefly the objectives of the CRVA process, the framework that we use, and I will be also showing you some of the outputs that we produce using GIS modeling. So on this slide that you can see now, on the left-hand side, we've got, well, I'm showing you two different hazards. On the left-hand side, there is a road that has been affected by soil erosion. This was after a storm during rainy season in Bangladesh. This was last year. And on the right-hand side, we've got an urban road flooded by heavy rainfall, probably a flash flood. This picture is from Dominica from January this year. So the purpose of the CRVA process, which I was saying, it stands for Climate Resilient and Vulnerability Assessment. The outcome of the CRVA process is to produce a cost-benefit analysis or capital investment program of the interventions that we propose to make infrastructure more resilient to the negative impacts of climate change. This is done by analyzing historical weather data, such as rainfall, changes in temperature, sea levels, and we also use climate baseline and future climate change projections. It is essential to look at the country's standards and codes, so we can incorporate and recommend climate change principles into the existing policies. So the methodology that we use in our projects is consistent with IPCC. I'm sure you know IPCC is the Intergovernmental Panel on Climate Change, which is a UN body for assessing climate change. You may be familiar with the diagram on the right-hand side of the screen. This diagram shows the overlap between hazards, vulnerability, and exposure within the framework, which determines the level of impact and risk at a particular location. So we follow a series of steps to develop our methodology. The first step is assessment of exposure. Exposure are the road transport assets that are at risk of being affected by climate variability and change. In our case, that we're in this presentation studying road transport infrastructure, it could be bridges, culverts, critical facilities such as educational or health facilities, emergency shelters, and so on. The second step is assessing vulnerability parameters. Vulnerability is the propensity of the infrastructure assets affected by hazards and their ability to respond. In our case, indicators could include design and construction information, for example, road condition and type. We also use social components such as population, employment rates, gender ratios. Step number 3 is the assessment of hazards. A hazard, as you know, is the potential occurrence of a climate-related physical event. It could cause loss of life or damage and loss to property or loss to infrastructure also. Types of hazards that we normally look at are landslides, storm surge, riverine, or fluvial flooding. Step number 4, identify risk hotspots. So we define a hotspot as the resulting area which has great exposure and vulnerability to the negative effects of hazards. The hotspots are modeled using GIS, ArcGIS, and they are the result of an algorithm which includes exposure, vulnerability, and hazard data that we have assessed in the previous steps. So I'll be showing you later some outputs of the GIS modeling. Finally, steps 5 and 6 are related to the adaptation and mitigation interventions that we proposed on the hotspot areas identified under step 4. The cost-benefit analysis would be the final step of the process, which leads to policy-making decisions. This is basically for the governments to decide if they want to invest in the interventions proposed. Application of the CRVA framework. So for each project, we need to tailor the CRVA framework to the characteristics and needs of our road transport network. As I said, we work in different continents and different regions of the world, so it's essential to tailor all the indicators to each region. So we start visiting the areas of a study. So normally the whole team is mobilized to the site. We analyze the type of hazards that affect infrastructure. And we need to collect all the shapefiles and data sets that relate to the data to be modeled into the GIS platform. This data is either collected firsthand or we use secondary sources, for example, public sources online. And the following slides show the outputs, some of the outputs of the CRVA and GIS mapping. So I've got a map for exposure mapping. So on the left-hand side, it's this is St. Lucia in the Caribbean. So we're studying the roads in red and the transport assets that are at risk of being affected by climate change. This is a very basic map. Vulnerability mapping, this is Guyana in South America. We're studying this map, the relationship between disabled population and the vulnerability of the roads that provide access to critical facilities, such as health or educational facilities. We also look at alternative routes to evacuate disabled people in the event of a natural disaster. Hazards. So I've got a couple of samples from the British Virgin Islands and Guyana again. On the left, we've got a map showing baseline conditions of storm surge hazard. This is for the island of Tortola. It shows the water levels that can be reached in case of coastal flooding caused by either a tsunami or a tropical cyclone, for example. On the right, we've got future climate conditions, in this case for a 100-year return period. This is the hazard of a study's riverine flooding. So the different areas in the red scale indicate the level of flooding that that particular area. And finally, I wanted to show you some hotspot modeling results. These show the most vulnerable areas of that particular road corridor. And these areas, as I said, are the most exposed to the negative effects of climate change. So this, the last slide, response to the climate resilient interventions. These are the potential intervention options that we propose for each hotspot identified. As I explained, this is just an example. So this, of course, needs to be tailored to each hazard and hotspot result. And so as I explained earlier, and to wrap up this presentation, the final step of the climate risk and vulnerability assessment is to produce a climate investment plan. So that's all from me. Please drop me a line if you have any questions or would like to get in touch, and thank you for your attention.
Yes, sure. Excellent, Nuria. Very interesting. For example, I have some questions about what you have seen, what you have showed to us, but later we will have time. Please keep there. Now, Edwar, it's our following speaker, Edwar Andrés Forero-Ortiz from the Water Technology Center CETACUA here in Barcelona. Oh, my video. I'm sorry. Yes, restart. I'm sorry. Edwar Andrés Forero from the Water Technology Center here in CETACUA, here in Barcelona. Edward is has an academic background in water engineering, hydroinformatics, applied and computational physics, and data science. For 10 years, he focused on the modeling and design of urban water systems, urban resilience, flood risk, and mitigation.
Thank you, Elisabet.
Edgar, can you hear me? I'm sorry. Well, please, Edgar, you can start. Time for you.
Okay. Good afternoon, everyone. I'm Edward Forero from CETACUA Water Technology Center. I will share my screen. This research was possible with the assistance from CETACUA, TMB, and Aquatech. Flooding events can produce significant disturbances in underground transport systems within urban areas and lead to economic and technical consequences, which can be worsened by variations in the occurrence of climate extremes. Within the framework of the European Project RESCCUE, climate projections for the city of Barcelona manifest meaningful increases in maximum rainfall intensities for the 2100 horizon. So a better comprehension of these impacts on metro urban systems and their conditions is consequently needed. Climate change endangers the Barcelona metro system when subjected to flooding events. As you can see in the attached video, flood events have caused property damage along with service disruptions by the invasion of underground infrastructures, such as these metro tunnels and facilities. Therefore, it is essential to evaluate flood risks in metro systems, plan for flood disasters, and set mitigation strategies efficiently. Barcelona Metro Line 3 is the line most vulnerable to flood events due to extreme rainfall, according to Barcelona Metropolitan Transport, the leading public transport operator in Barcelona records. Hence, in this study, the Metro Line 3 is integrated into a 1B2D hydrodynamic model developed for the entire drainage system of the city of Barcelona. Water presence in the tunnel and the stations of the metro system affects the continuity of the service. Thus, this research central network components into the hydrodynamic model through the creation of hydraulic geometry elements comparable to real infrastructure components, evaluating a conceivable water in the system.
I'm sorry, Edgar,
Yeah.
I'm sorry, because I don't know what is happening, but after you put the video, there is some problems connections. Perhaps I propose to the panelists, the technical assistants to help us. Perhaps, can you propose?
Okay.
I'm sorry, Edgar, but it was difficult to follow you.
Okay, Edward, try to speak now, please.
Can you listen to me?
Yeah, now it's working perfectly.
Yeah,
you can keep on going. Thank you.
Okay, thank you. I will follow with the next slide, okay? Okay, the railway signaling equipment is qualified to work under wet conditions. Therefore, the circuit could work in case of flooding. Depending on the amount of water in the surrounding area and its conductivity, it may complete the electric circuit. Then diverting the electric current between the power supply and the receptor. Sorry.
Edgar, I'm sorry to interrupt you again, but they are telling me that there are some problems with hearing you correctly. I don't know if yes, I'm sorry to interrupt again.
Don't worry, don't worry. I don't know what is happening.
Okay, now it's perfect.
Yeah, okay.
Yes, you can follow.
Yeah, I think, sorry, I think it's because of the presentation. So maybe could you unshare your screen and I will share the presentation for you? And
yeah,
you
sure.
can tell me
Sure,
next,
sure.
and I will pass the yes, thank you.
Yeah, okay. Yeah, could you start from that slide, please? No, yeah, that one. Okay. This research incorporates Barcelona Metro Line 3 real data into the hydrodynamic 1D 2D model of Barcelona, considering the connections among possible water inflows and metro tunnels and stations, and considering them as pipelines. As you can see, our model considers the dynamic model implementation, the Metro Line 3 data acquisition, and components and data introduction processes. Furthermore, the model calibration and validation process, along with flow risk assessment under the impact of the climate change. Next, please. This study defines risks according to the interruption of the metro service as a result of rainwater flooding on the urban transport system. Encompasses the combination of hazard and vulnerability.
Edward, yeah. I'm sorry, but they proposed me to stop here your presentations. They are going to try to arrange what is happening. We don't know. It's when you are speaking. We can listen very badly. And we are going to introduce the other speaker. During that time, you can try to manage or to arrange, I don't know what. So let me introduce, but stay here. Stay here because you will be with us. We want to listen your conference. Now we are going to listen María Pregnolato. She's from the University of Bristol. María is a lecturer of the Civil Engineer University of Bristol. She's investigating the impact of flooding on bridges and transportation, looking at enhancing the infrastructure resilience. So I think that María is going to introduce another point of view, it will be very interesting to listen what you are doing in the University of Bristol. Please, Maria, time for you. You have also 10 minutes, and we will try to come back to Edgar later. Please, thank you for being with us.
Thank you very much. Can you hear me well and see my screen?
We can hear perfectly, and we can see your screen. Thanks. Perfect.
Good afternoon, everyone. Thank you for the introduction. I'm Maria Pregnolato. I'm a lecturer at the University of Bristol. And my research is about modeling road networks according for the impact and the resilience to flood risk. And actually, my approach is quite similar to what has just been presented to Núria before. So it started from the concept of risk in the traditional way, as composed by the three elements: hazard, exposure, and vulnerability. Considering also the consequences, so the losses in terms of direct consequences, such as the cost of a repair and replacement, but also the indirect consequences, such as the rerouting of traffic, the impact to the environment or to the heritage, and so on and so forth. So what I'm going to show you is the application of a flood transport model in which the elements of the risk, hazard, vulnerability, exposure, and consequences are fed into through various data sets, such as the road data and the traffic data for the exposure, the flood maps for the hazard, the key receptors for considering critical infrastructure, such as hospitals and schools, and so on and so forth. And this flood transport model allows to identify a different range of analysis according to the complexity and the computational demand that is possible to achieve through the equipment. So for example, examples of high-level analysis could be the mapping of vulnerabilities and hotspots in the cities, accessibility analysis to key receptors, as well as the road of particular links, such as bridges in the network. Another example of analysis for a further improvement of the resolution would be try to understand which roads should be kept operational during, for example, emergency management or rescue plans, or looking at the impact on particular categories or particular means of transport, such as, for example, public transport. Again, if we want to enhance even more further the analysis, we can arrive to test adaptation options and to study strategic road networks from the point of view of implementation, testing new routes, and applying more sophisticated transport model able to account for congestion, rerouting, traffic lights, user choices, and so on and so forth. And this model can be looked and used through different lenses according to the interest of the user, such as climate change, sustainability, adaptation, mitigation, and other options. So the model essentially works in layers, again, as was shown also in previous presentations. So we have the layer of the exposure in which we can input the information for the exposure layer, that in my case would be the road network. And so the road type, the speed, the capacity of the road. And then there is the hazard layer in which we have the intensity, duration, and frequency of the flood scenarios in terms of probability and return period. And then the vulnerability layer in which the hazard layer is put in relationship with the exposure, like for example of a curve that is taking into account flood depth as intensity measure and is able to compute the safety speed for vehicles to drive through flood waters. And I also develop a bit further the first layer, considering also bridges as particular elements in the network. Within the model, there are also some tools kind of hidden. So for example, a risk matrix is applied in order to understand the most critical spots within a network. And these critical matrix account for the exposure in terms of the flow according to automatic traffic sensors, so the number of people passing per certain links or during the day, and the hazard, that is how much flood water can we expect according to the scenario considered for each stretch of roads. This because we can have roads in the countryside that are very flood prone, but that not many people are using them, as opposed to links on the highways that are perhaps not very prone to flooding, but used by thousands of people every day. And so this matrix is a very quick tool in order to identify the most critical and vulnerable stretches of roads. And this has been applied to Newcastle, which is a city in the UK in the north of England. And we identify 6 stretches of road that we're considering of high criticality, but we map all the major roads of the city center. And this type of analysis are very useful if you consider, for example, emergency plans during urban planning, but also evacuation plans or rescue plans for public buildings such as schools and care homes and so on and so forth. The same model was also applied in Italy to a neighbors of Florence, which is Galluzzo. And here we did 2 separated analyses considering different type of vulnerability. So we studied the vulnerability of parked vehicles using the flood, speed and depth. And we look also at the vulnerability of traveling vehicles in order to map, again, the vulnerability of roads. And this was actually very interesting because we work quite closely with the civil protection of the city, which is used to have an annual exercise in order to understand their preparation, people awareness, and actually the most impacted areas of the city. So it was good to have a sort of feedback from them after the exercise, and also to see if this type of tools can actually be useful during emergency planning and emergency preparedness. For the same area, we also studied the accessibility problem using what are called the serviced areas. The serviced areas are these 3-colored area, and they are also called isochrones because they underline all the points that can be reached by the same amount of time. So for example, for the baseline scenario, that is the scenario without flooding, from the city center of the city, that is the black and red spot, it is possible to reach all the points within the green areas. And this in particular includes all the hospital and the fire station of the surrounding. After 20 minutes of the onset of the flooding event, when floods start to spread throughout the city, from the city center, you can see that the accessible areas has reduced and is just the orange area. But the accessibility is still fine because most of the hospitals are included in the serviced area and all the fire and police station. However, if the plans delay in their operation, and so we get to T2, that is 40 minutes after the onset of the flooding event, is it possible to see how the service area has shrunk dramatically and all the hospitals and fire stations are outside the service areas. And that means the city center is very difficult to be accessed and is almost isolated. So I think this is another good tool for decision makers and planners during emergency. And finally, I'm going to present what I recently done, considering particularly the role of bridges in the UK. This is Carlisle, a city again in the north of England, in which we have an historical city center with 3 different bridges connecting different parts of the cities of different age, different characteristics. So that has caused like problems in the rerouting during flooding. And so we started to study the M6 bridge, that is the bridge owned by the highways. And the green path is what you can see as the straightforward path to go from one side to the other side of the city using the highway. However, if this bridge is damaged or is considered not safe enough to be used during a flood event, there are 2 options. So the options on the left, that is the orange path, is what would be recommended to private vehicles. And you can see that not only the route is longer, but it will take also 4 times the expected journey traveling time. And I have also to underline that this is a very low complexity model. So this is the very best case scenario in terms of traveling time, because no congestion, no traffic lights are included. So only free flow speed is assumed for this simulation. And heavy vehicles can go through the historic center of Carlisle, especially because the Eden Bridge is an historic bridge. So they would be rerouted through the Warwick Bridge. And you can see how their journey will increase even further in length and time, again, without considering potential congestions and other issue linked to a more dynamic simulation of the traffic. And I think the case of the bridges and an holistic view of the road network is very interesting when we consider indirect and direct consequences. And in this case, the direct consequences would cover the consequences for repairing the bridge to cleaning the debris. And indirect consequences would include the detouring of the traffic and the delays, for example, for businesses. Other things that can be considered could be like intangible losses, such as the damages to heritage in case of old bridges or old structure, or also the damages to the environments in terms of pollution for the increase of the length of the journeys. Other interesting perspectives are, for me, the cases of interdependencies, when, for example, we have bridges carrying utilities such as water pipes or electricity cables. And here is really a sort of a hub for infrastructure interdependencies. So just to summarize, like what I presented, I was thinking it was useful to share with you. It is the integrated model for flood transport analysis, the attention paid to road network resilience in terms of criticality and transport accessibility. And finally, the importance of certain links over to others, like, for example, in the case of bridges. I thank you for your attention, and I'm looking forward for the discussion at the end of the session. Thank you.
Thank you, Maria. Thank you, very interesting. We have seen how you can connect your assessment with the response, with the civil emergency agents, and also with other utilities. It will be very interesting if somebody have questions. I remember that if you want to make questions to the speakers, please write a short sentence, a short questions, because it's a pleasure to have these 5 speakers with us. I invite you to make questions or to prepare the questions for later. Now, let's go with Geomilie Tumamao. She's coming from the University of Filipinas. A short brief about Geomilie. She's an experienced architect and a urban planning researcher, serving as a lecturer at the University of Philippines. She currently leads a collaborative research development and networking initiatives of the Office of Research and Publication at the University of Philippines and Urban and Regional Planning. So welcome, Geomilie, please, time for you. You have as the other speakers, and I can explain that later we will turn back with Edgar. So let's go, Geomilie.
Thank you. Can everyone hear me? Okay. Thank you.
Yes, very well.
So, mabuhay, warm greetings from the Philippines. Ensuring that public funds are invested in life-saving facilities that are efficient and cost-effective to construct, operate, and maintain, as well as resilient to disruptions brought about by climate-related hazards and sea level rise, starts with science-based decision-making. Geospatial analysis can support governments through risk-informed planning. In a study conducted by the UNDRR, 346 disasters were reported in 2015, which affected 98 million people and costed about $66 billion in economic damage. Asia has the highest number of reported disasters, with China, Indonesia, Philippines, India, Pakistan experiencing most of these disasters. In the last decade, disasters killed 1.3 million people and left further 4.4 billion injured, homeless, displaced, or in need of emergency assistance. With the majority of fatalities being due to geophysical events, 91% of all the disasters were caused by extreme weather events. 6 years ago, the IPCC predicted with 95% certainty that global warming will result to greater risks of severe, pervasive, and irreversible impacts for people and ecosystems by amplifying existing risks and creating new risks for natural and human systems. This will worsen the suffering of those in the margins, where essential infrastructure and services are actually lacking. Located in the Pacific Typhoon Belt and the Pacific Ring of Fire, the Philippines' more than 7,000 islands is uniquely exposed to a plethora of hazards, including recurrent typhoons, earthquakes, and active volcanoes. Typhoons actually caused the largest number of losses in terms of life and property in this country. On average, 20 tropical cyclones enter the Philippine waters each year, with approximately 8 to 9 making landfall. This is predicted to escalate based on recent models showing that rainfall increase will likely happen in Luzon and Visayas, while Mindanao or South will experience decreasing trends. In 2013, Super Typhoon Haiyan, dubbed as the worst typhoon in history, cut a deadly path across Visayas and battered the eastern coast of Samar Leyte, as well as the southern coast of Samar and eastern Samar. Tacloban City in Leyte, which is the economic hub of that region, registered the highest number of losses during its onslaught. Among the issues found were related to disaster supply chains. And these are delayed relief operations days after the impact due to damaged transportation networks and communication, inadequate supply levels, poorly coordinated delivery of relief supplies, especially at the last mile distribution, and wastage of supplies due to inadequate and poorly situated warehouses. These experiences indicate some of the weaknesses in the design of disaster supply chains, which, when left unresolved, exacerbate the suffering of affected sectors. Given the importance of having well-conceived, constructed, and managed physical assets that can withstand the impacts of hazard events without significant damage or loss of functionality, researchers from the University of the Philippines focus on Tacloban City as one of the largest and hardest hit areas by Typhoon Haiyan. Using probabilistic models, the city's critical point facilities and road infrastructure networks, which provides key support services in times of crisis, were assessed for exposure to the following climate-related hazards: sea level rise, flooding, storm surge, and rain-induced landslide, using geospatial analysis. A multi-criteria site selection process was also used to see possible alternative areas where these facilities and routes may be relocated. Okay. The risk maps generated for the study were based on the following assumptions: 100-year rain return period for flood hazard maps, a 4-meter maximum tide height for storm surge, a 1.5-meter maximum tide height for sea level rise as determined by using probabilistic models in the existing literature. These maps were geospatially manipulated with healthcare facilities, evacuation facilities, administration and management buildings, as well as transportation and communication facilities, which comprise the critical point facilities and routes of the disaster supply chain in the area. In the assessment of critical point facilities, it was found that many of these are at high and moderate risk of storm surge and multi-hazards, meaning that this should be considered for possible transfer or strengthening. sea level rise threat is minimal as long as the level do not exceed 1 meter. However, it is worth noting that Tacloban City's only airport will be affected by sea level rise if the tide height exceeds 50 centimeters. Using network analysis, the study also traced the flow of goods from the main hub to the distribution hubs, where these are processed, repacked as needed before being sent to various distribution outlets, such as evacuation centers, barangay halls for food and non-food items, and healthcare facilities in the case of medical supplies and equipment, where beneficiaries will gain access to aid. A total of 1,427.5 kilometers of roads comprising the disaster supply chains was overlaid onto the hazard maps to determine the extent of its exposure to those various climate-related hazards. We found that when combined, more than half of its 411 routes are exposed to these hazards. This finding actually ties neatly with 2013 reports and partly it explains why the disaster supply chain broke down in the aftermath of Typhoon Haiyan. This also suggests the need to consider both redundancy and resiliency related strategies in rebuilding these physical assets. To determine the suitability of other locations for these critical point facilities and the possible alternative routes, a multi-criteria analysis using GIS was also carried out in a two-step process. A cursory approach, removing all of the hazard-prone areas within the city boundaries was done on the first try. This yielded potentially suitable areas for consideration, which are spread out in 97 barangays and account for about 5,738 hectares of the total land area of Tacloban City. To ensure that the new areas where these disaster supply chain facilities will be constructed will not encroach on lands that are earmarked for protection or productive uses, the second GIS overlay excluded the following land uses and characteristics from the potentially suitable areas, which are forest zones, protected areas, areas with steep slopes, environmentally sensitive areas, built-up areas, strategic agriculture and fishery zones. And this yielded 2,541.92 hectares of environmentally suitable areas that are spread out in only 36 out of 138 barangays. The conduct of this exposure analysis on the assets comprising the disaster supply chain of Tacloban to various climate-related hazards can provide decision makers a risk-informed decision support tool that facilitates local governments' resilience to disaster risk in 3 ways. It allows them to know more about their risk options. It teaches them how to invest wisely and build more safely, with due consideration to the relevance of the priority services and operations being carried out in these facilities before, during, and after a disaster. Truly, climate resilience will require rethinking the way we decide how we shape our cities and how science and technology should be used to serve our people. And with this, we thank you for this opportunity to share our work towards a resilient Philippines. Thank you.
Thank you very much, Geomilie. Just in time. I didn't need to ask no one speaker to stop before they have consumed their time. Now we have time to come back to Edward. Please, they have told me that you can manage now to continue to follow with your presentation.
Yeah, that's it.
Thank you. Perhaps you can finish in 5 minutes, perhaps. I don't know. Yeah. Or do you want to come back? As you want, Edward.
Okay. I will try to keep it short, okay? As I can. Okay, continuing. The water presence in the tunnel and the stations of a metro system affects the continuity of the service. So this study represents metro systems components into a hydrodynamic model through the creation of hydraulic geometric elements comparable to real infrastructure components, and evaluating them as a conceivable water entry point into a system. For example, as you can see in the images, the station entrances and the ventilation grates were modeled into a hydrodynamic 1D, 2D model. What is happening? Okay. Sorry, I'm having some troubles. I don't know why. Wait, okay. This study incorporates Barcelona Metro Line 3 real data into the hydrodynamic 1D, 2D model of Barcelona, considering the connections among possible water inflows and metro tunnels and stations, and considering them as pipelines. Our model considered the hydrodynamic model implementation, the Metro Line 3 acquisition, data acquisition, and the components and data introduction processes. Besides, the model calibration and validation process, along with the flood risk assessment under the impact of climate change. We use the risk concept similar to other previous presentations, defining risks according to the interruption of the metro service as a result of rainwater flooding on the urban transport system. The concept of risks used in this research uses the combination of hazard and vulnerability. Hazard, as we can see, is characterized by flooding water depths as the intensity of the hazard along the metro tunnel, and it's related to design storms of different return periods. The vulnerability criterion focuses on the ridership number affected by service interruption. For the hazard assessment, 1, 5, 10, and 20 years return periods were used as inputs for the Barcelona hydrodynamic 1D, 2D coupled model for this study. So the operational thresholds, which defines metro service operation, is the water depth within the metro tunnels, as you can see in the slide, and through operational experience and base of technical assumptions with support from TMB, the hazard range are defined as shown, as likewise with the vulnerability assessment. The vulnerability data was used using the user entrance data reflecting the ridership flow, defining peak flows and off-peak flows. According to our calibration and validation processes, the first set of analysis examined real events, pluvial fluid impact. And these real pluvial impact flooding events were comparable with some synthetic fluvial events. Well, as results, for various return periods, including the line 3 infrastructure points number, where water accesses are identified, the maximum water depth in the 2D elements surrounding water access points, and the maximum water depth projected in metro stations, tunnels, for scenarios with climate change influence or without it. Here we can see a metro station's risk assessment map for synthetic events at scenario with climate change influence. In this case, a 20-year return period event, T20CC. We can see a hazard map considering future flooding conditions with climate change influence, the vulnerability map applying peak ridership flow, and the risk map with flooding water depth. The findings presented here highlight the considerable influence of water depth in the water entry point surrounding areas, when assessing the climate change impact upon flood risks. Well, as an outcome, we can see how the small difference between the maximum water depth affecting the water entry points to the metro system, comparing the TO5, the 5 years climate change event, with the 20 years climate change scenario, produces significant differences for the risk assessment results. We have a significant risk for 14 stations in 5 years climate change scenario, but this scenario is increasing to 20 stations, having a significant risk in 20 climate change scenario. Therefore, it seems necessary to incorporate a range of approaches in adaptation measures that are focused on coping with this increment in the water depth. So finally, our findings draw attention to the importance of considering that the low level of some ventilation grades at metro stations accesses may increase probabilities for water entering in flood events, as you can see in the figure. The outcomes of the study display that by accounting for increased possible water entry sources, water depth range forecasts in metro tunnels widen. It is reasonable to assert that the principal source of flooding is a local level phenomenon of water entry. Thank you so much. You can contact me through these ways, and thank to the URCC.
Thank you very much, Edward. Well, I can see that you have perhaps 15, 20 minutes to make questions, and we have some questions. Let me read carefully because I don't want to make mistakes. The first question is for Núria Biosca. I have this impression because, let me read. In the climate risk and vulnerability assessments, there looks to be a massive amount of data to collect for the hazard mapping. How do you combine all the hazard data together to make a single map? Núria, have you heard my question? I think that this is for you, about the data, no? About how to combine the data. Mm-hmm.
Yes, I have the question. Thank you, Elisabet. Well, basically, all the data is processed into the GIS platform. So for those who are familiar with GIS and Saga and GRASS softwares, they know that, so once you collect data sets and shapefiles from either ministries, or if you do drought condition assessments on the ground, for example, so you just need to export all the databases into GIS, so you can create your either raster or shapefiles, and all the files are combined into the software. So, for example, data that we normally use is the DEM, so the digital elevation model, which gives you all the contour lines to have the elevation levels of the roads. In this case, we use geographical information. We use, in the case of road transport sector, so we use road data, so where the bridges are, where the culverts are. It's a very, I'm not a GIS expert myself, but I understand a little bit how the software works. But it's about combining all the right files into the software, and then through an algorithm. So for example, for the hotspots mapping, we create what we call a risk index, and we just select a few indicators, such as vulnerability indicators, social indicators, and we combine them into a formula or algorithm, which is called on GIS, and you just need to run the model. I think for those who understand GIS, hopefully they are following what I'm saying. Unfortunately, I don't have the software on my laptop right now, so I cannot show you how to run the model. right now, but I'm happy to give you further information if you wish. Yeah.
Yes.
Hopefully this was helpful enough.
Yes, yes. No, this is a huge difficulty or a huge problem. No question. If you are collaborating with Caribbean countries or with I don't know. No, you have explained this such as cities. Perhaps you don't have as many information, as many data organized as you want, and you need to spend a lot of time, a lot of effort to put together. I think that this was a question not only for your case, but also in general for all the initiatives that have present the other speakers. And we have another question from Mark Violet. This is a question for Maria Pregnolato. Please, Maria, let me see. Well, first of all, he says, thank you for your interesting presentation. Do you include structural reliability indicators for bridge? If yes, how? Thank you.
Yeah, thank you for this question. I think it's actually one of the most interesting aspects when you put things together. And I mean, like the functionality of the roads and the structure of the bridges. So actually, at the moment we are doing this case study in which we are starting from flood simulation and we are trying to arrive to the functionality of the network. And the delicate part is, of course, try to translate the hydrodynamic loads into damage for the bridge and functionality loss. So we are going to publish the paper soon, and essentially we have considered for categories of damages that then translated in a sort of functional loss for the bridge. So try to merge the gap between, you know, the structural damage of the bridge and then the decision making from the side of the operator. So try to understand which damages can be associated for a bridge closure or when the bridge is safe to be used. And we use some categories just to describe a low, medium, moderate, and high damage of the bridge. And these are associated with certain categories that regarding like the condition of the piers and the joints and other things like this. And if you want to drop me an email, I can even send the preprint if you're interested in this.
Mm-hmm. Yes, probably you will receive an email. Well, I think that we have to speak about bridges. That is a problem generalized all around. Although in Europe we have very sad experience on that, and also I know in other parts of the world. And but I would like to make a question to Luis. Luis, can you hear me? Because if I'm not wrong, you are the only authority. You are the authority from the Metropolitan Transport System in Barcelona. So you can share with us another point of view. You have explained that there is a model of governance to introduce, to develop, to implement this huge plan. Could you please speak for the audience a little bit more about that? Because we have a model, we have measures, we know what we have to do and how to manage all the agents involved on that.
Well, thank you, Elisabet, for the question. The way we decided to manage the infrastructure actions is different the way to manage the more soft or mobility actions. The way we decided to manage the infrastructure action was two ways. One, to introduce in the planning, in the projects and all the process of the new infrastructures, the climate change as not as an externality, more as a question that you have to solve during the project. That later you are going to have the externalities if you don't do the things, okay? And regarding the current infrastructures, we decided to study what we have explained in a broader way, and then introduce in the planning of the infrastructure of the region the climate change actions as a as a
control perhaps? No.
What?
Control perhaps to
no,
control,
not control.
No,
It's an action by itself. Because later on, when we decided that there is a problem in an infrastructure, we make the appointment for this specific infrastructure. So we lose the plot with the way what was happening. So now we have decided to build like a measure that is explaining all you have to do, and then you can follow all the actions on that measure. Because if not, you lose what is happening. Because then when you arrive to the Generalitat, the Catalan government, to the workers, they have a lot of work to do. So they decided to do what you say, but you lose what is happening at the end. So as you put that as a new measure, we are obliged to follow the measure until the end of the measure.
Yes, that's like this is like a project management system, no? Yeah. A project management
that's the idea.
Approach, also to follow and to introduce. It's a very interesting solution. I hope that it has been also interesting for the other parts of the table. We have another question. Let me see. It's in general. This is, you can share your opinion, feel free. To all, yes, for everybody. What will be the most urgent risk for transport infrastructure that you face? So now pay attention to this word, urgent, a priority. Now, tomorrow. Please, who wants to answer? The most urgent risk.
I think I can answer that. For the Philippines, we are like the gateway for a lot of typhoons. So any hydromet risk is our most urgent concern regarding transport infrastructure. And therefore, any aftermath of any typhoon event or even just the high tide event is a problem for us. When hydromet risk is combined with sea level rise, then you can actually imagine how devastating it is, given that our country is ranking 6 among all countries internationally in terms of coastal of length, and our cities are in coastal areas majority. So this is a very difficult problem for us because we, in other areas they don't have water, but in the Philippines we have too much of it at certain times, and that's something that we have to plan for, manage, and try to build resilience from. Thank you.
Thank you, Remy. Somebody else want to answer? What is the most urgent risk?
Well, maybe no, maybe in the Barcelona region, maybe it's flooding. Maybe flooding, especially sea level and flooding because rainfall in our coast, because rivers, because we have a very short rivers with a high that they have a high level of water when it's raining. Maybe, but I must say that we are not facing the problem in that way. We are facing the problem in a short-term way. Not what is happening tomorrow. It's more like what is happening more in a long-term, medium and long-term.
Medium
term.
If not, there is another question here in the chat for Edward. Please, you have explained us how you manage about one of the lines, no? And you have made decisions or take decisions. Could you please explain if you are going to translate or to put the same methodology for other parts of the transport systems? Will you please explain the next steps to explore other lines or other parts of the system?
Thank you, Elisabet. Our methodology can be adapted to any underground system, transport system, even a mine, even anything else related to transportation at underground levels can be started through this approach, because this is one of the strengths of our model. It can be adaptable to anything. So the main criteria is having flooding events in order to have this validation and calibration processes. And besides that, we also need a 1D or 1D, 2D coupled hydrodynamical model in order to modeling the area in the aspects of water and hydrodynamical behavior.
Wonderful. It will be very interesting to see how you and the other speakers are sharing and giving this knowledge to other parts of the world. And this is a question. I have a question for Geomilie, because really, when I have seen in your screen that you have 20 siphons per year, isn't it? Well, really, I can imagine if you are solving one, you are preparing the other, and perhaps you are managing 2 or 3 at the same moment. I don't know, I'm exaggerating a little bit, but how are you managing the long-term, the science, the data, the model, at the same time that you are solving this huge number of siphons per year? Please, a little bit summary.
Yes, thank you for that question. So the science part is the easier part, because you have models to sort of inform the decision-making process. You have, and Philippines is very well studied because everyone knows how a lot of geological and climatological risks are interfacing in that country. However, the more difficult component is the political part, because communicating the science to decision makers require that you have to sit with them, and really it doesn't have to be at the top, and you also have to start at the bottom also. So you have to have a very layered approach, no? So on one hand, you're talking with decision makers, you're talking with politicians, but on the other hand, and the more important matter is communicating it at the bottom, at the grassroots level, so that the people who will be affected the most will understand what they will go through, because it is not a question of if, it is a question of when. We're saying that the science is already there. It doesn't matter. It's only a question of when this will hit you. So, but the difficulty in that is because of the uncertainty. A lot of people think that because it has not happened yet, it will not happen in the future. So you will have to have a lot of hand-holding. You will need to really break bread with your communities, and you really have to lobby at the bottom so that they will, again, help you lobby with their mayors, lobby with their politicians to pass the laws needed to improve conditions, because it will affect them. And at the end of the day, they are the voters. And so long as they know that they can demand better service from the government, that they can demand, and they should demand it from the government, you have a leverage, sort of. It is not an easy process, because that means that on one hand, you need to talk on a technical manner, but on the other hand, you have to make science relatable. You need to turn it into stories that are easy to chew, easy to understand, and more importantly, it should hit the heart and the stomach of the people. And that is something that I have been slowly learning as a very difficult process, because I have always been very technical in most of my practice.
Experience, yes. So it's difficult to explain science to politicians. It's also harder, difficult to explain science to the society in general. So very interesting your approach. And let me, if you don't have any questions, I want to make a question to Maria. You have shown us Maria Pregnolato, you have shown us that in Newcastle, you have used what you are preparing, what you are modeling to share with the civil protection agents during the emergency. I think that it was quite interesting, this approach, and this is like something quite useful or quite new. Could you please, Maria, explain if what you have been doing in Newcastle should be done in other cities to use what you are doing for the emergency response?
Yeah, we co-work with the Civil Protection Local Agency for, we were in Florence actually, and it was quite interesting because they have this system there in which they sort of pre-plan the actions that they want to do, and then they have annual exercise in which they try to do the operation that they would be supposed to do during an emergency context. And so for us, it was interesting to double check which roads they consider to be particularly vulnerable, which areas they are worried about, how they spread the messages and the awareness to citizens. And I always recommend to work closely with a city council or a regional agency, because we have really feedback for about the inputs, actually what they need, what can we do to help them, as well as some data in cases. So it was a very successful collaboration, and this is my approach, is quite always like a two-way communication with practitioners. Could be a bit time consuming because they don't have much time in most of the cases to spend with you, but it's very rewarding, and you have really this sensation that what you do, it's useful and transformative. So I recommend that.
Thank you. Yes, probably the word is collaboration, and since the beginning, not at the final of the process, although since the beginning. Well, if nobody has no more questions, we are on time, well, 4 minutes later. I'm going to close the session. Thank you very much to all the speakers. Thank you very much to the audience for your questions. I have the impression that you have been speaking about science, about data, about modeling, about assessment, introducing the future here, putting the future here in our table. So before the COVID, the pandemic, we saw that the climate change was the huge challenge for the humanity. And now we have also the climate change is there. When we wake up after the COVID, after the pandemic, we will see that the climate change is asking us and to putting in our face that it's a huge challenge for the humanity. I hope that that's all. And I don't know if the managers of the screen and technicals will close the session. Thank you very much.
Thank you very much.
Thank you so much, Elisabet.
Thank you, Elisabet. Thank you.
Bye-bye, Maria, Luis.
Thank you, everybody. Bye-bye.
Bye. Bye-bye.
Bye.